Next up, Degioanni comes back to the stage to talk about advanced application debugging.
I'm going to spend the next 30 minutes to talk about tracing, as in transaction tracing, based on tracing as in system call tracing. So my talk is already becoming confusing even before I start. So as I was mentioning in my welcome speech this morning, there are a few things that we pushed out in Sysdig as, let's call them experimental features during the last few months. One of these is a functionality that we call tracers, and essentially makes it possible to inject custom markers inside the Sysdig event stream and do fun stuff together with it. So I want to tell you a bit about how it works, and then give a few demos interactively in my Linux virtual machine. Before we do that, a bit of context on this. So Luca showed these diagrams this morning as well. This is the basic Sysdig capture diagram. We have a kernel, we have a bunch of processes on it, we have processes that can sit inside containers, and it doesn't matter. Sysdig is able to essentially, through the kernel module, to capture the system calls and system events, and then consume them and create a stream. The stream looks, and now you're familiar with it, looks a bit like a sequence of operations that the different processes are doing on top of the kernel. So Sysdig is able to dump them to disk, filter them, let you analyze them, and all of the fun applications that we've seen in the previous demos. Sysdig tracers are a way to actively inject events inside the stream. These events can be used to mark the beginning and the end of what we call spans. So through tracers, you can essentially mark the beginning of something and the end of something. What something means is arbitrary, because it's inside your code or your scripts. But examples of what you can convert into spans is function calls, requests, or any arbitrary piece of execution inside your code. Tracers are usable from any language. In particular, the trick that we use to implement them is you write something to /dev/null. While using /dev/null instead of something else, when we started working on that, we first experimented with creating a custom device to collect this information, like in /dev. But then we also wanted this to be container friendly, which is one of the bullets on this slide. So we want containers to be first-class citizens in this kind of functionality. And dev/null is always there. It's available no matter what. Even in the simplest possible container, dev/null is always there. So if you can write to dev/null, you can emit a Sysdig tracer. And if you do it from inside the container, we're still able to capture that write, and we're still being able to inject it inside the stream. The other goal is low overhead instrumentation. So this is not, let's say, as low overhead to go to something like a profiler. That's not the primary goal of this, but it's low overhead enough that if you are tracing a distributed application, especially a containerized application, this should be completely negligible. So we had as a goal being below 1 microsecond in overhead to emit and collect these tracers. So in practice, going back to the list of system calls that I was showing before, it's possible to essentially write to dev/null and start having these red events that are interjected with the rest of the Sysdig stream events. And then you can just consume them the usual ways you do with Sysdig. So you can print them on screen, you can create cheesers on top of them, you can do a bunch of stuff. Events always come in pairs. So you always have an enter event and an exit event. And the combination of an enter event and an exit event with the same ID and the same name is a span. Spans you can have multiple spans inside one or multiple applications running on the same machine or multiple machines. And it's possible to create a hierarchy. So you can have parent spans that contain child spans. So in practice, this allows you to implement something similar to stacks, right? Because you can arbitrarily go essentially deep inside your code or inside your application and create a stack out of that. The format is, we have a couple of formats, but essentially you do text writes to dev null, and then the Sysdig capture driver is able to interpret these and convert them into the proper events. And there's a simple format that is just a text string with columns as separators, and you have essentially the direction, ID, arbitrary number of tags, and tags also define the hierarchy, and then arguments. So, for example, if you're creating a span of a system call, you can have the enter or the input or output arguments of that function call converted into span arguments. Or there's a JSON format that is a bit less efficient, but it's a bit more versatile, especially in the kind of strings that you can use. The simplest possible example is tracing of shell scripts. So I know it sounds sort of crazy as an idea, but this is pretty much an example of APM for a bash script. And what this does is pretty self-explanatory, but this is essentially a pinger script that goes and curls the Sysdig website in a loop. And essentially what we do is we start a span just before the curl, and we close that span when the curl is done. So essentially we are measuring in a loop how long does it take to download the sysdig.org web page. Before I go into examples, a sort of somewhat limited list of fun things you can do with tracers. Measure latencies in your code. In particular, as a developer, many times you want sophisticated ways to get stack traces or latencies, and there are many powerful tools to do that. But very often, I just want to throw a quick measurement in my code. So how long does it take on average to run these requests or stuff like that? And tracers want to be a really user-friendly way to do that. And then, as I will show you in the rest of my presentation, we offer a bunch of tools that allow you to filter, visualize, or display this information. You can save them to trace files, exactly the same way you do it with Sysdig, and they go in trace files with the system events. So you can analyze them with both the text-based Sysdig and Sysdig. You can inspect system activity inside the execution spans. I will show it later, but the system events are intermixed with this. So you can create filters, and you can see what happens just inside one portion of your code. And do a bunch of other stuff like log monitoring that is trace-based, or latencies, test the output, and a bunch of stuff like that. All right, so that's the context. Let's go into my virtual machine. Is this readable? Should it be a bit bigger? Yes, no, yes, okay. Actually, this is the same script that I was showing before. Actually, I have two versions that are currently running on my machine. One is pointing to Sysdig, the other one is pointing to Google. Okay, so I can go back to my shell and do something like just applying a filter for the tracers, and I can essentially use Sysdig to filter and look at those tracers. Of course, I can use the Sysdig filtering syntax to do something like and span dot tags equal Sysdig, and I can essentially use exactly the same filtering languages to manipulate tracers, and in this case, I'm excluding the Google ones, and I'm only showing the Sysdig ones. I can customizing the output. And in this case, instead of just showing the standard command line, the standard line output for Sysdig, I'm printing the duration of the span as a human-readable string, and the filter is still on the Sysdig. So I'm looking at the ballpark of how long it takes to ping, to curl the Sysdig website. As you can see, sometimes it takes very long, 5 seconds now. So that is a quite good indication that the network here is pretty crappy. Another way to observe the same thing is using Sysdig. And in particular, what I'm going to do is I'm clicking on F2 to go to the views, and then I'm going to the bottom. There's a view that is called tracy spectrogram. So we've discussed the spectrogram representation multiple times today. It's one of the ones that Brendan showed during his presentation. By the way, look at the network here. So let's pause it for a second, because this is interesting, actually. I can see in the spectrogram, so what I'm doing is, now this spectrogram is limited to just the tracer. So I have spans, I have 2 things running, right? Google and Sysdig. And they are doing requests. Every time one finishes, we are mapping it in the spectrogram. The spectrogram has time on the x-axis. So, and then the color is how many hits I get in the time interval. And every line that scrolls down is a different half a second, right? So we are essentially seeing the progression of the spans. And we clearly see 2 different vertical bands. Okay? And then we see once in a while a clusterfuck. You see, there's something that is in the 10 milliseconds and something that is in the 100 milliseconds, and then everything goes to hell once in a while. I was already observing this morning, and so I actually took a trace file. So this shows that you can save. You just do a Sysdig -w, and you write everything to disk, and then you can just reopen the file and apply the analysis. So this is just a trace that I took this morning on this network. So let's go back down to the tracy spectrogram. And this shows the behavior, essentially. So a 10 to 50 milliseconds band, an 100 plus millisecond band, and then once in a while a clusterfuck area. So one functionality that I introduced in Sysdig spectrogram is the drill down capability. So I can use my mouse. This is a terminal, by the way. So it's quite brand damage to work with the ncurses library to implement mouse, and it still doesn't work well on Mac. It gives me headaches, but it's pretty fun. So I can zoom in an area and click on it, and I see essentially the spans that are in that area. So the first area is Google, as you can see. I can go back and pick a bit of the slow area. The slow area is Sysdig, so Google wins, essentially. I don't know how Google can be better at delivering their website than Sysdig, but they are. Now, if we go in the clusterfuck area, it's a bit of Google and a bit of Sysdig. So that's a clear indication that once in a while, every, I don't know, like 20, 30 seconds, the network here goes a bit nuts, and everything becomes slow, you know? So even Google, that was much faster before, now it's as slow as Sysdig. So that's a good, interesting use case of very trivial. Again, let's go back to the script. It's just a matter of echoing something, you know? So even as I was saying before, there's sophisticated stuff that you can do as a developer, but very often you just want to measure basic stuff, and a trivial method like this with a bit of visualization on top can help you. And visually things, pop up much better. Of course, you also have the option of being more sophisticated. So one thing that you can do is -c tracers to SysD. So this is a chisel that just a Lua script that takes filters on tracer information, extract the spans, and then just sends all of the information out as SysD. So for example, I'm running it now. I also have the Sysdig Cloud Agent running on the same machine. So this thing is piping statsd to localhost, and the Sysdig Cloud Agent picks it up, and then I can go in my Sysdig Cloud user interface, and I can see that I have a Google and the Sysdig, and here, essentially I can see my thing collected in a centralized place, and I can, for example, easily create an alert on top of these if I want. So we go from instrumenting a shell script with just a write to dev null to being able to pipe it to a centralized monitoring system with, just essentially a single command line. All right. So this is essentially the basic functionality. Now, what I'm going to do is I'm going to run a script, a Python script. Actually, let me show you the script first. This is a bit big. OK. Now it's a bit small. We have a bunch of community created libraries to essentially leverage this functionality from inside your scripting languages without having to actually physically write to dev null. I'm using a Python one here, and I'm essentially decorating a Python script. As you can see, I import the tracer library, and then what I do is I can use the with syntax in Python to decorate a piece of code as I want to trace it. So everything inside this with will be traced as read. And I'm creating a Python script because I want to show the hierarchical capabilities of this. So as you can see, I have 3 high-level spans here. One is read, the other one is process, and the third one is write. And process actually has 2 subspans. So this shows essentially how this can work in a hierarchical way. Let's start the script. And if I go back, actually, let me go to Sysdig. And this time, I'm picking a view that is called traces summary. So this gives me an overview of the traces that are being generated in this system, and gives me the average time, the minimum time, and the maximum time for these traces. I can also see the number of childs, so I can see that process as childs. And I can just select it, click enter, and now I'm inside it. And so it's a bit like hierarchical navigating a stack. As you can see, with language support, this comes pretty natural and allows you to essentially do a drill down exploration of something that could be a bottleneck in your application or inside your code. So that's basic concept of hierarchy, and I can see it event.type equal tracer. I can see how it works. Essentially, Python is generating. Let me actually do and proc.name equal Python. So I filter out the curves, and I can see how Python creates, some spans that are basic spans and some spans that have a hierarchy, and then Sysdig is able to pick that up. Now, there are a couple of things that are interesting that we can do at this point. The first one that I want to show you is, of course, you can do something like span dot tags equal write, and at this point we only get the tracers that correspond to this span. But there's also another syntax which is eventin.span.tags. And now what we do is we have Sysdig that is filtering, and it is emitting only the system calls that are within the spans that respect the filter that I provided. So this is sort of we know that Sysdig, by default tends to be pretty verbose, and this essentially allows you to limit the output and what you get from Sysdig to specific portions of your code. So it's like putting, again, application tracing together with system call tracing. And the concept is pretty basic, but it's pretty powerful. So I want to show you a couple of things that you can do with it. The one that you can do is apply chisels to the specific filters that you have. So if you look at my simple Python script, I actually have a log function that writes data to app.log, and then I have logs in different points of my application. So I can actually do something like Sysdig and apply a chisel like spy logs. And spy logs essentially looks at every log that is written in the system, both to syslog or to files that end in .log or f.log in their name. So as you can see, it's pretty verbose. At the same time, I can apply this chisel to events that are in a specific span. So now I'm looking at the logs that are generated in a specific span of my code. So logging in the context of something that you have defined that is happening inside your application, either if it's a local application or a distributed application. I'm very fascinated by this concept. I think it's much more powerful than just this demo. So what I did was I put together a visualization for this. I worked together with one of Sysdig's front-end engineers to try to find an interesting and creative way to put everything together in something that is nice to see. And I actually implemented also a relatively more complex microservice-based demo in which this is the Sysdig cloud map of the demo, essentially. So I have a movie theater application with users and movies, and then there's a tier in which there's a user manager, a movie manager, and the cache, and then the movie manager goes to a queue, and everything goes to the database, okay? Let me see how this shows. This is the flame graph representation of the same infrastructure. So this is multi-container. I did the work of essentially passing the tags and the IDs across multiple containers. So that requires a bit of work because you need to be able to, either in an HTTP header or something, pass your tags to the next tier if it's multi-container. And then I collect everything. This is essentially the multi-container flame graph of our movie theater application. So Brendan is sitting here with us. This is, one of his signature contribution to the world of tracing and performance management. I'm sure that all of you are aware of how a flame graph works. They are a powerful tool that many of us use. But to summarize, essentially, we're seeing, well, first of all, here we're seeing two different entry point transactions in this little microservice application. One is called users, and the other one is called movies. And we have 10 calls for each of them. I'm selecting the average one, so I'm selecting users. So this is the whole time that user takes, and these are the different components, so the different successive calls. And the color here identifies a container. So by looking at the color, I see how the tree of calls goes from container to container. Okay, so I can look at the average time, but I can also take the slow transaction, the fastest transaction, or the slowest transaction, and I can see how they compare. Now, this is the users. If we look at the movies, we see that the average is 700 milliseconds. The minimum time is 400 milliseconds, and then the maximum time is very slow. It's 2.5 milliseconds. So I can click on the slow one. And one thing that I've implemented in this flame graph is you can click on any of the spans in the visualization, and at the bottom you can see the logs that have been emitted on the span. So I can essentially explore transactions, and I can click around, and I can see what are the logs in the different pieces. So it's like flame graph and transaction monitoring plus the logging. And it's interesting because, well, by the way, I have two options. One is this span only, and the other one I can also look at the childs to essentially get a view that includes the childs of this span as well. But let's go back again to our movies and to our slow one. If we look at the logs, we can see that the movie queue span has an error which says database connection lost. And after that, you can see reconnecting to DB and connecting to DB, which takes essentially 2 seconds, which is also most of the time of this transaction, which also corresponds to the maximum time that we're seeing here. So the slow transaction here seems that like it's being caused by the movie queue container losing the connection to the DB and then reestablishing the connection, which we can see pretty well here. So, by the way, this is not this is more like a weekend project, this visualization. But if somebody finds it interesting, I will be happy to clean it up and push it on GitHub together with the other chisels. But it's just a chisel that collects this information and then packages everything in a web page with a bit of the tree code. This is essentially how much time I had for this. You find more information online. We have a pretty decent manual on the Sysdig wiki, and we have integration for Python, Node, and Go that you can go grab on GitHub as well and start experimenting with this. I promise you, it's pretty fun. Thank you.
As always, we have time for a few questions if we have any from the audience.
So for the filter you did for the event in span.tags, what kind of logic is it using to determine what is eligible to be within the span? Is it just time-based? Is it more?
Yeah, that's the most complicated part of the code, essentially. And it looks at, first of all, at the tracer enter and exit tracer properties, so ID and tag. It also looks at, by default, at the thread that is emitting that specific span. But you can customize it. If you look at my script here, as you can see, the ID that I gave is PP, which means parent process, which works well for scripts because it's essentially that tells that you want to get all of the events that are in this process or in the parent in the processes that have the same parent process. So you have, depending on what you write here, you can put a number here as the ID, and at that point you have your unique transaction ID, or you can use a couple of these acronyms. One is T and is for thread. The other one is P and is for process. The other one is PP and is for parent process. And this influence is essentially for this specific span, which events will fall in the event-in filters.
Any last questions? All right. Thank you, Loris.
Thank you.